I'm Daniel Su from Columbia University, and I'm presenting a joint paper with Tosh from Columbia and Akshay Krishnamurthy from Microsoft Research. This talk is about representation learning. We focus on the task of making certain supervised learning problems easier after mapping data from the original input space to a new feature space. For example, data from two classes might be hard to separate in the original input space, but they might become linearly separable after mapping to the feature space. And we hope to learn a feature map with this property from data. We study representation learning in a semi-supervised learning setting. The idea is to use a large number of unlabeled examples to learn a useful feature map, and then given this feature map, to use a small number of labeled examples to learn a simple predictor on top of this feature map. The first step will be done using something called self-supervised learning, as we'll explain shortly, and the second step is called the downstream prediction task. Self-supervised learning is a generic two-step strategy for learning representation from unlabeled data. Step 1 is to learn to solve an artificial prediction problem called the pretext task. For example, with unlabeled image data, one may learn to predict the color channel from the grayscale channel. And for text data, one may learn to predict a missing word from its context. These are made-up prediction problems for which the unlabeled data already contains information to supervise a learner. Step 2 is to use the solution from step 1 to derive a feature map, which we denote by phi. When step 1 is solved by training a neural network, a popular choice for phi is to use the same neural network without the final layer. The specific form of self-supervised learning that we study is called contrastive learning, where the pretext task is the problem of learning to discriminate between naturally occurring pairs and completely random pairs. For example, in text data, a natural pair could be two snippets from the same news article, while a completely random pair could be snippets from two randomly chosen articles. To solve a contrastive learning problem, we start with unlabeled data, automatically form these separate classes of examples, and then provide this data to a supervised learning algorithm. Then we somehow derive a feature map from the predictor learned by that algorithm. Contrastive learning has been rather successful in a number of application domains. For example, when the contrastive learning method called SimClear is applied to unlabeled ImageNet data, we get a feature map on top of which linear classifiers achieve near state-of-the-art performance for the ImageNet classification task. Moreover, these linear classifiers needed only around 10% of the labeled data to be effectively trained, so the hopes of semi-supervised learning are realized in this case. Of course, the feature map provided by SimClear, or that of any other contrastive learning method, cannot possibly be useful in all downstream tasks. So the question we want to answer is, for which downstream prediction tasks should something like contrastive learning be useful? In our paper, we identify a condition called multi-view redundancy and prove that it's sufficient for contrastive learning to be useful for a downstream prediction task. Suppose this downstream task to predict a target variable y from an input x. We proved that if the unlabeled data has two views, x and z, each with near optimal mean squared error for predicting y, then a feature map phi of x learned using contrastive learning enables linear functions of phi of x to achieve near optimal MSE. Note that the two views in their original representation may only be useful for predicting y via nonlinear predictors. So the benefit of contrastive learning is that it provides a feature map on top of which linear functions are just as powerful at predicting the target. In the rest of the talk, I'll describe the specific way we formalize contrastive learning and derive a feature map from a solution. Then I'll describe the multi-view redundancy assumption, and finally, I'll give the formal theoretical results and some of the proof ideas. We use the following formalization of contrastive learning, which has appeared in a number of prior works in various guises. Here, x and z represent two parts of an unlabeled example, and we assume that they are drawn from some joint probability distribution. The goal of contrastive learning is to learn to discriminate between positive examples, which are pairs drawn from the joint distribution, from negative examples, which are pairs drawn from the product of marginals. A common way to do this is to try to estimate the odds ratio function, denoted here by G star, which gives the ratio of the conditional probability that a given pair is a positive example to the conditional probability that a pair is a negative example. When we train neural networks, say, with cross-entropy loss to solve this classification problem, we are implicitly estimating this odds ratio function. Without lots of generality, we can assume that the estimate is trained from an equal mixture of positive and negative examples. Now I will describe how we derive a feature map from a solution to the contrastive learning problem. Let g hat be our estimate of the odds ratio function. Our feature map, phi hat, is defined as follows. We obtain m points called landmarks, each of which is the z part of a random unlabeled example. Then, for a new point x, phi hat of x is defined to be the m-dimensional vector whose ith feature is the output of g hat on input x paired with the ith landmark. This way of forming a feature map is essentially agnostic to the way that the contrastive learning problem is solved. Now I will present the multi-view redundancy condition. At a high level, multi-view data have distinct views that are each useful for predicting a target Y. For example, if the goal is to classify scientific articles by their topic, one view might be the abstract of the article, and another view might be the introduction. Each view is supposed to be useful for predicting the topic of the article. In their seminal work on co-training, Blum and Mitchell explain why the popular bootstrapping methods for semi-supervised learning work under the assumption that the two views are conditionally independent given the target. This work spurred a number of other theoretical analyses of multi-view learning methods. The one that's perhaps closest to our work is the study of canonical correlation analysis by Cockaday and Foster. They show that if the best linear predictor of a target from a single view is nearly as good as the best linear predictor based on both of the views, then one can essentially, without harm, apply linear dimension reduction based on CCA to a potentially lower dimensional subspace. And this in turn reduces the sample complexity of supervised learning. It is remarkable that there is no explicit assumption of conditional independence between the two different views. Instead, this notion of linear multi-view redundancy is sufficient. We take inspiration from this work and ask what can be done if the two views are redundant but only via nonlinear predictors. So instead of using CCA to derive a feature map, we'll use contrastive learning. Now, finally, here's the formal definition of epsilon multi-view redundancy. It says that the best possibly nonlinear predictor of Y based on a single view should have mean squared error only epsilon more than that of the best predictor of Y based on both views. The key idea in our work is that under this assumption, it suffices to approximate a certain surrogate predictor, mu of x, that is nearly optimal for predicting Y given x. Here, we can roughly interpret mu of x as predicting Y from x via an intermediate prediction of a certain function of z. And this function of z is the best prediction of Y based on z. So this key idea is borne out in this lemma, which says that the surrogate predictor has mean squared error only 4 epsilon more than that of the best predictor of Y based on both of the views. So it suffices to show that this surrogate predictor can be well approximated by a linear function on top of the feature map provided by contrastive learning. To see why this is the case, we first observe that the surrogate prediction of Y given x can be rewritten using a change of measure based on the odds ratio function g star. This is because the odds ratio is really the same as a certain density ratio between the joint distribution of x and z and the product of their marginals. Here, we're using the fact that the contrastive learning problem has positive and negative examples presented in equal proportions. Next, we approximate the expectation via Monte Carlo. Assuming that the landmarks are drawn IID from the marginal distribution of z, this expectation is approximately equal to a sample average, where each of the terms in the average involves an evaluation of g star at x paired with one of the landmarks. Finally, by defining the feature map phi star accordingly, we see that this sample average is a linear function of the feature vector phi star of x. After taking into account the Monte Carlo error, we conclude that with high probability, the surrogate predictor is well approximated by some linear function of phi star of x, and thus this linear function, in turn, has near optimal MSE, with only order 1 over m additional error. There is one important catch, though, which is that this feature map phi star is based on a true odds ratio function g star, rather than an estimate of it. So we also prove an error transform theorem, which relates the quality of the learned feature map phi hat to how well we solve the contrastive learning problem. For concreteness, this assumed that the objective used in the contrastive learning problem is the cross-entropy loss. We proved that essentially the same bound that we showed for phi star on the previous slide also holds for phi hat, except now the right-hand side has an additional term that's proportional to the excess cross-entropy loss of g hat compared to g star. The theorem says that the ability to solve the downstream prediction task with linear functions may improve as we get better solutions to the contrastive learning problem. This is something that is in fact borne out in real data experiments with contrastive learning. In summary, our work shows that a generic multi-V redundancy assumption can be used to theoretically justify contrastive learning. Our work is part of a broader agenda to understand modern representation learning methods used in deep learning through the lens of probabilistic modeling. We believe that this approach can lead to new insights about these methods that are grounded in well-understood modeling assumptions, and eventually suggest new forms of representation learning for new applications.